Okay, Assalamualaikum and hi everyone. So today we are going to continue with 5.2 Alkene, part B. So let's see the learning outcome for part B. Okay, first one we are going to show the preparation of alkenes through the dehydration of alcohol, and then we are going to look at the dehydrohalogenation of haloalkene. So the dehydration of alcohol means that we need to remove water to form alkene, and also we need to remove, for haloalkane, we need to remove one hydrogen atom as well as one halogen atoms to form alkene. Okay, then we are going to write the mechanism for the dehydration of alcohol, and then we are going to justify the major product formed using Caesar rule, and last but not least we are going to deduce the major product of elimination reaction. Alright, so let's get started. Okay, now let's look at the first method to prepare of an alkene. So the first method used is the dehydration of alcohol. So this method is actually the principal method of preparing alkene in the laboratory. Alright, so one hydrogen atom and one hydroxyl group will be removed from the adjacent atoms from an alcohol to form an alkene. Alright, so this reaction will be carried out by heating the alcohol with excess concentrated sulfuric acid or phosphoric acid to form an alkene. Alright, so this concentrated sulfuric acid will be act as the catalyst and dehydrating agent to form an alkene from the dehydration of alcohol. So beside sulfuric acid, we can also use phosphoric acid as the acidic catalyst. So the relativity ease of alcohol to undergo dehydration is from the tertiary alcohol. So tertiary alcohol is the easiest to undergo the dehydration, followed by the secondary alcohol and the primary alcohol. Alright, so for some alcohol, water can also be eliminated from adjacent carbons in more than one way. For that being said, that means that we can form more than one product. So for example, we can form major product as well as minor product. So for us to differentiate which one is the major product and which one is the minor product, we are going to use the Caesar rule. The Caesar rule stated that in elimination reaction, the major product is the most stable alkene, commonly the most highly substituted alkene with greater number of alkyl group attached to the carbon-carbon double bond. So maksudnya, lagi banyak lagi number of alkyl group attached to the carbon-carbon double bond lagi, dia akan disebut sebagai major product. Okay, so now if we compare between these two products, okay, so this one has 1 and 2 alkyl group attached to the carbon-carbon double bond, while for this one it only has 1 alkyl group attached to the carbon-carbon double bond. Okay, since this product has more number of alkyl group attached to the carbon-carbon double bond, hence this product is the major product and this product is the minor product. Okay, now let's look at the example for Caesar rule. So we have 2 butanol here. So upon undergo the dehydration of alcohol, it will form 2 product, where the first one is 2-butane, where this one is the major product, and the second one is 1-butene, where this one is a minor product. So here, let's look at how this major product and minor product is formed just by predicting from the alcohol here. So we know that we have to eliminate the water to form an alkene from the alcohol, right? So now we have to remove one hydrogen and one hydroxyl group from the alcohol. So we know that we have to remove this hydroxyl group from this carbon. So the question is which hydrogen that we need to eliminate to form the double bond. So we have 2 choices. The first choice is here. This hydrogen is the secondary hydrogen because it is bonded to the secondary carbon. Alright, and the second choice we have is this hydrogen, where this hydrogen is the primary hydrogen because it is bonded to the primary carbon. So if we were to eliminate the hydrogen from the secondary hydrogen here, we are going to form the double bond between these 2 carbon. So this is actually the major product 2-butene. Alright, however, if we were to eliminate the hydrogen from the primary hydrogen here, we are going to form the double bond between these two carbon, which means that we are going to form this product, which is 1-butene, where this is the minor product. Alright, so we can conclude that if we eliminate the hydrogen from the higher class, example from the secondary or the tertiary hydrogen, we are going to form the major product. Alright, but if we were to eliminate from the lower class of hydrogen, for example the primary hydrogen, we are going to form a minor product. Alright, so let's look at this major product. Okay, if we eliminate the secondary hydrogen, this product will be formed. Okay, so why is this product is a major product? So according to Cesar's rule, that the major product will have more alkyl group attached to the carbon-carbon double bond. So here we have 1 and 2 alkyl group attached to this carbon-carbon double bond. Okay, while for this 1-butene, we only have this 1 alkyl group attached to the carbon-carbon double bond here. So this is the minor product, so this is the major product. Alright, because this one has more alkyl group attached to the carbon-carbon double bond. Alright, now let's look at the reaction mechanism for the dehydration of alcohol for 2-butanol to form 2-butene, which is the major product. Okay, so the first step for this reaction mechanism is the protonation of alcohol. So in the presence of strong acid, the OH group in this alcohol will form bond with this hydrogen from the acid to become protonated. Okay, so if we see here, this alcohol will form bond with this hydrogen so that it will become protonated with positively charged oxygen here. Alright, and it will leave the acidic catalyst with a negative charge here. So this acid catalyst will be used again in the step 3 later on. Alright, now let's look at the second step for this reaction mechanism. So for the second step is the formation of carboxyl ion. So we want to form carboxyl ion. So let's look at the bond between this carbon and oxygen here. So this bond will be break, okay, heterotically. Alright, so both of the electron here will be transferred to oxygen and leaving behind the carboxyl ion here. Alright, so water will be leaving this molecule. So now we have the carboxyl ion, alright, attached to this carbon and water. Alright, now let's look at the last step for this reaction mechanism. So for the last step, we need to eliminate this hydrogen from this carboxyl ion molecule. Alright, so we have the acidic catalyst from the first step earlier. So this acidic catalyst will attack this hydrogen, alright, and form bond with this hydrogen. So this hydrogen will be eliminated from this carboxyl ion molecule, and then the 2 electron from this carbon hydrogen will be transferred to this carbon-carbon bond to form the pi bond. Alright, so now the alkene will be formed. Alright, now we have already completed the 3-step mechanism for the dehydration of alcohol. So now let's look at the summary of the mechanism for this reaction. So please remember that the first step you need to do is to undergo the protonation of alcohol, where your hydroxyl group will be attacking the hydrogen from the acidic catalyst, alright, to form protonated alcohol. Alright, and now you will remove the water to form a carboxyl ion for your second step, and then you need to remove the hydrogen, alright, so to form the major product. So it means that the secondary hydrogen will be eliminated. If we want to form the minor product, it means that you have to eliminate the primary hydrogen from this carbon. Alright, okay, now there is one extra step for the mechanism of dehydration of alcohol, where we undergo some rearrangement or shifting, alright, during the dehydration of alcohol. So some of the primary and the secondary alcohol will undergo the rearrangement to form a more stable tertiary carboxyl ion, alright, to form a major product. Alright, now let's look at the step for the rearrangement during the dehydration of alcohol. So the first step and the second step are pretty much similar to the previous example, but for before we proceed with step 3, there is where the rearrangement occurs, where this less stable secondary carboxylic ion will rearrange to form the more stable tertiary carboxylic ion. So the rearrangement occurs through the migration of group from the carbon atom adjacent to the carboxylic ion. So because the group shift from the one carbon to the next, so this kind of rearrangement is often called a 1-2 shift. Okay, so the first one we have 1-2 methyl shift, where we shift the methyl group from one carbon to the next neighboring carbon. Or we have 1-2 hydride shift, where we move the hydrogen from one carbon to the next neighboring carbon. Alright, this is all to form the more stable tertiary carboxylic ion. So now let's look at the example of the 1-2 methyl shift, where for this example we want to shift this methyl group to this carbon, alright, so that we can form the tertiary carboxylic ion. Alright, now let's look at the reaction mechanisms that involves the rearrangement, where it has 1-2 methyl shift right before the third step. Alright, so for the first step and the second step is pretty much similar to the previous example, where we know that the first step, the alcohol needs to form a bond with the hydrogen from the acidic catalyst to form a protonated alcohol here. And now in the step 2, we have the removal of water to form the carboxylic ion. So the carboxylic ion that is formed from the step 2 is actually the secondary carboxylic ion. So now, right before we move into the step 3, this is where the rearrangement occurs. So here, we want to form more stable tertiary carboxylic ion. So from the secondary, we want to form a tertiary carboxylic ion. So we have the methyl group at the neighboring carbon of the carboxylic ion. So this methyl will shift to this carbon, alright, and the positive charge here will transfer to this carbon. So it's actually like swapping between the methyl and the carboxylic ion punya charge. Okay, so now the charge for carboxylic ion will be transferred to this carbon, and the methyl group will be transferred to this carbon. Alright, so now we will form the tertiary carboxylic ion here. Alright, now we want to form the alkene, so we need to eliminate the hydrogen from the neighboring carbon. So we can either remove the hydrogen from this carbon, or we can either remove this hydrogen from this carbon to form double bond. So this hydrogen is actually the tertiary hydrogen, and this hydrogen is actually the primary hydrogen. So if we were to form the major product, we need to eliminate the hydrogen from the tertiary hydrogen. So if we eliminate this hydrogen, alright, so we will form the double bond here. Alright, so we will form the major product, alright, where there will be 1, 2, 3, 4 alkyl group attached to this carbon-carbon double bond. Alright, however, if we were to remove the hydrogen from this carbon, and the double bond will be formed here. Alright, so now the number of alkyl group attached to the carbon-carbon double bond will be only 1 and 2 alkyl group. Alright, so this one will be the major product, and this one will be the minor product according to the César rule. Alright, now that is for the 1-2 methyl shift. Now we want to look into the example for the 1-2 hydride shift. Alright, so let's look at this example where we want to form this product. So we want to form the double bond inside this cyclohexane. Alright, so the first step is pretty much similar. We want to undergo the protonation of alcohol. So this alcohol will form bond with this hydrogen from the acidic catalyst, alright, to form the protonated alcohol. Alright, and at the second step, we want to remove this water to form the carboxylic ion here. Alright, so now the carboxylic ion that is formed here is actually the second carboxylic ion. Alright, now this carbon here, alright, the carbon from the neighboring carbon of this carboxylic ion, alright, has one hydrogen here. Alright, so when we shift this hydrogen to this carbon, alright, this carbocation, this positive charge will be transferred to this carbon. Alright, so we call it 1,2 hydride shift. Alright, so now this carbon here, so this carbon from the cyclohexane will have the positive charge. So this one is the positive, this one is the carbocation, tertiary carbocation. Alright, so now we want to form the double bond inside the cyclohexane. So we need to eliminate the hydrogen from this carbon. Alright, because we want to form double bond here. So we need to eliminate this hydrogen. So we use the acidic catalyst. Alright, so this acidic catalyst will form bond and with this hydrogen, and this hydrogen will be eliminated, and this single bond from the carbon hydrogen will be transferred to this carbon-carbon bond to form pi bond. Alright, now the double bond alkene has been formed here. Alright, so this is the example for the 1,2 hydride shift. Alright, now we already finished talking about the first method of preparing an alkene, which is the dehydration of alcohol. Now we want to look into the second method, which is the dehydrohalogenation of alkyl halide. So the alkyl halide is also known as the haloalkane. Okay, so the dehydrohalogenation of alkyl halide means the removal of one hydrogen atom, alright, and one halogen atom from the adjacent carbon of the haloalkane. Alright, so this reaction must be carried out by heating the haloalkane with an alcohol, alright, with of the bases. So mesti ada alcohol and base. Alright, so this method is also followed the Caesar rule to form major and minor product. So now we want to eliminate this bromine. So now the question is which hydrogen we want to remove to form major and minor product. So let's look at the class of hydrogen. So this hydrogen here, alright, is the secondary hydrogen, alright, because it attached to the secondary carbon, alright, and this hydrogen here is the primary hydrogen because it attached to the primary carbon. Alright, so you know that if we want to form the major product, we have to eliminate the hydrogen that is of the high class. Alright, so we want to eliminate the secondary hydrogen to form the double bond here so that we can form the major product here. Alright, so this major product has 1 and 2 alkyl group attached to the carbon-carbon double bond here. Alright, now if we were to eliminate the hydrogen from the primary hydrogen, alright, we will form the carbon-carbon double bond here. Alright, so we will form this product here. So for this product, we only have 1 alkyl group attached to this carbon-carbon double bond. Hence, this one is the minor product. This one is the major product according to the Caesar rule. Now, let's look at the last example for the dehydrohalogenation of alkyl halide. So we have this molecule here. So we want to eliminate 1 halogen and 1 hydrogen, alright, to form an alkene. So we know that we have to eliminate this bromine here. So now the question is which hydrogen that we should eliminate to form major and minor product. So between this hydrogen or this hydrogen here. Alright, so this hydrogen is the primary hydrogen and this hydrogen here is the tertiary hydrogen. Alright, so if we were to eliminate this hydrogen from this primary hydrogen, we are going to form double bond here. Alright, so the product that will be formed is this product, which is the minor product. Alright, but if we eliminate the hydrogen from this tertiary hydrogen, we are going to form a double bond here. Alright, and the product that will be formed is this product, which is the major product. So let's see why this is the major and why this is the minor product. So this is the major product because it has 1 and 2 alkyl group attached to the carbon-carbon double bond. Alright, while this one only has one alkyl group attached to this carbon-carbon double bond because this carbon only has hydrogen. Alright, so this one has 2, this one has 1 alkyl group. Alright, so according to Caesar rule, we know that the most stable alkene is where they have more alkyl group attached to the carbon-carbon double bond, and that one is the major product. So this one is major product according to Caesar rule, and this one is the minor product. Alright, so I think we have finished the 5.2 alkene part B. Alright, so we are going to stop the video here, and we are going to continue with part C in the next video. Alright, so thank you for watching. So we'll see you again in the next video. Bye. Assalamualaikum.